Share screen. Okay, cool. So, right. So last time what we did was we proved that there's an equivalence between trees and dividing chains. Okay, so what does that look like? We can just scroll up and see what it says. So if you have an ordinal alpha, the following two things are equivalent. One is that you have a collection of formulas indexed by alpha and a tree of height alpha and a collection of numbers, one for each number less than alpha, such that you can build a tree of tuples of height alpha. The paths of this tree are consistent. You know, you plug the thing at level 0 into the 0 formula, the thing at level 1 into the 1 formula, the thing at level 2 into the 2 formula. That gives you a consistent partial type. And if you look at some node along the way and you look at its immediate descendants and plug those into the formula at the corresponding level, that's going to be ki plus 1 inconsistent, or ki plus 1 is the level at which you're plugging things in. So that gives you like a tree. It's exactly like the tree property, except the k and the phi can vary with the level. And two, there's a sequence of numbers indexed by alpha, or sorry, parameters indexed by alpha, and formulas. And the I plus first formula divides over everything that came before. Okay, so that is an equivalence. These two things are the same. And how did the proof go? Well, the way the proof went was if you have a tree, you can make it S indiscernible. And if it's S indiscernible, then if you look at the things at level I plus 1, they're indiscernible over the path below them. And also the formula is inconsistent at that level, so that means it divides. So you get dividing over the path below, and that translates into the dividing chain. Namely, you can take the 0 path, the all zeros path in the S indiscernible tree, locally based off of the tree that you're given to get a dividing chain. Then given a dividing chain, you can build a tree using many automorphisms. Because when you divide, you move along an indiscernible sequence, all those things have the same types. There's an automorphism taking one to another, and that tells you how to move. So there was a kind of process of building trees using automorphisms, which we did down here. Okay, so let's just take stock of some consequences.
I have a quick question. So are the tuples A eta all of the same length?
No. And okay, so this is a good point. When I was developing generalized indiscernibles, I sometimes said same length tuples, but in fact, you don't need that. And if you have an index model which has a unary predicate in it, then the unary predicate can hold of some things and not hold of some things, and those two things will never have the same quantifier free type. So there's no reason actually that they need to have the same length. So we can talk about S indiscernible trees where the tuples at different levels have different lengths, and that's totally fine. I should have said that explicitly when we were doing generalized indiscernibles.
Okay,
I also have a question about the proof from yesterday. We were doing like this transfinite induction, and we didn't worry about the limit stages. But I was thinking that at the end of each successor stage, at the end we didn't we take like we use the modeling property and we change the tree. But if we do that at each stage, then when we get to a limit, what do? We can't take the union of the previous trees.
You do compactness. So
okay,
I mean, what you do is you write down a type in the variables indexed by the elements of the tree that you want, and because each finite piece we'll talk about, the tree somewhere up, some initial segment of the tree in question, you can realize it.
Okay, thanks.
Yeah, that's a good point. So this really only handles the successor step. You have to say something for the limit. Okay, that's a good point. Okay, were there other questions? No? Okay, so let's briefly take stock of some consequences. So the first one is there is no dividing chain of length greater than or equal to t plus. Okay, let's assume t is simple, sorry. So assume t is simple, then there's no dividing chain of this length. Why? Well, suppose you have one. So what do I mean by a dividing chain? I mean, I have a sequence of formulas, phi x, yi, I less than t plus, and a sequence of numbers, ki, I less than, oh, sorry, so sorry. Yeah, okay, let's say ki, I less than t plus, and ai, I less than t plus, such that phi I plus 1, x a I plus 1, k I plus 1 divides over a less than or equal to I. Now, what do I mean when I say ki plus 1 divides? I mean that it divides with respect to some indiscernible sequence, and the amount of inconsistency you get is ki plus 1. I mean, like if you have an indiscernible sequence and the instances of your formula are inconsistent along that indiscernible sequence, then they're inconsistent for some in. So let that in be ki plus 1. Okay, then by the pigeonhole principle, we can assume phi I equals phi and ki equals k for all I less than or equal to t plus. Less than t plus, sorry. Why? Well, because how many formulas are there? There are at most the cardinality of the language many formulas. That's the size of t. How many k's are there? Well, there are countably many. Languages are always countable because they include all of the formulas. So t plus is at least all of 1, which means that there is also 1k that has to occur cardinality of t plus many times. So restricting to a subset where I have the same formula and the same k, I find a sequence exactly like this where the k is fixed and the phi is fixed. So if you don't see how to do this immediately, first restrict to a subset of size t plus where the phi is fixed, and then apply pigeonhole principle again to get the k fixed. All right, so if you do that, then you apply the equivalence. To get that, to get that phi has the k tree property, and that implies t is not simple. So what is the tree property? The tree property is exactly the configuration we described above, coming from this pattern of dividing, where the formula is the same and the k is the same of infinite height. So that gives you the true property. And so that's a very easy consequence of this. Now, a consequence number 2 is if P is a type over some set A, then there is some A prime, which is a subset of A, such that A prime is no bigger than T, and P does not divide over A prime. Okay, so I should say, I'll always mean this unless I specify otherwise, but this is finitely many variables. Sometimes, I mean, later on, actually, we will have to worry about types and infinite many variables for taking Morley sequences and things in the Anisotropy 1 context. But for now, whenever I talk about a type without further specification, I'll mean that it has finitely many variables. Otherwise, you have to add in a parameter for the number of variables you have. But okay, so what does this say? So remember that we had two notions around. One way of thinking about dividing is that you don't divide over A. Not dividing over A means that all of the essential information is contained inside of A. So then we also had this other notion of generic extension. So if you have a type which is defined over one set, then a way of extending it generically to a bigger set, taking this extension, is that you say that you're not in any of the small sets that you can define with the new parameters. So you extend the type, and you also add the condition that you're not in any of the small sets. So we want to do that for forking. We know that we always can. But for dividing, in fact, we can also do it. Sometimes it works, sometimes it doesn't. And what this says is that we can always view every type as a generic extension of some type restricted to a small subset. So if you have some type, which is maybe over a subset of size all of 17 in a countable theory, then all of the information about the realization of that type will be contained in some small subset, some small countable set. And the way that you get the type from the whole set is by generically extending from the small set. So P, regardless of what it is, has the property that there's a small enough subset, no bigger than the size of the language, such that the type doesn't divide over that subset. So it's a kind of compactness principle. It says that all of the information is contained in something compressed. Okay, so how do you deduce this? So what we'll do is we'll say, okay, suppose not. Then let A0 be the empty set. So we know that P divides over A0, otherwise we'd be done, via some phi 0 x A0. And so we'll let A1 be what? We'll let A1 be the set that contains A0. You have to divide over A0 too, right? Because A0 is size no bigger than the size of the language. So P divides over A1. So notice that this is a subset of A because the formula comes from the type which is over A. So P divides over A1 via some phi 1 x A1. Then P divides over A2, which is A0, A1. Now, if our assumption fails, then we can continue and build a dividing chain of length t plus, contradicting the above. So let's draw the picture of what this looks like. You have a set A and you have a type over it. And you first look at the empty set. So that's going to be like A0. And you divide over that via some parameter A0. So you put that in to A1. And then you divide over that with some other parameter. You put that in to A2. And you divide over that with some parameter A2. And you put that into A3. And what you're doing is step by step, you're adding only finitely many parameters. And so the sets in question are still smaller than the size of the language, or at most the size of the language. Then at limit stages, you just take unions. And because t plus is regular, if you take a small union of stuff that's less than the size of t plus, then it will still be of size less than t plus, and so you can continue up through limits. And so this says that if you don't have a small subset over which you do not divide, then you can construct dividing chains of length t plus, and that gives rise to a counterexample to simplicity. It gives rise to a formula with the true property. So this is very well and good. And what we'd like to do is we'd like to extend this to non-forking, this principle. So this is called local character. So this is called local character of dividing, which is true in any simple theory. But what we don't have yet is that this is true for forking. And so that's what we will do next. All right, so in order to get to the same thing for forking, we're going to have to develop a theory of rank. And so I have notes on this. Let me find them. I think my notes disappeared, which is bad. I mean, I can wing it, but I really don't want to. Yeah, okay, it looks like we're winging it. Okay, so I did mention before the lecture even started that today might be not my peak performance. But anyway, I mean, okay, I think I remember how this definition goes. So this is what's sometimes called Shala rank. Although Shala calls it degree. And what's confusing is that there's something called Morley rank and a notion called Morley degree. And Morley degree has nothing to do with degree. And so people call it Shala rank. You should probably call it Shala rank. All right, so we're going to define d p delta k to be greater than alpha by induction on alpha. So we will define dp delta k greater than or equal to alpha, where p is a type, possibly partial. Delta is a set of formulas, and k is a number less than omega. All right, so what does this say? So the first condition will just say that dp delta k is greater than or equal to 0 if p is consistent. Okay, so if you put in x not equal to x, then you get rank -1, let's say. But I did say p was a type, and part of the definition of being a type is that you are consistent. So the rank is greater than 0 always. Okay, then the key condition is the successor step. So when are you greater than or equal to alpha plus 1? That happens if there exists a sequence ai I less than omega and a formula pxy in delta such that two things happen. So the first is that phi x ai I less than omega is k inconsistent. And if you look at the rank of p union phi x ai delta k, that's at least alpha. All right, so this is the successor step. And then for the limit step, we'll just say dp delta k is at least delta for delta limit if dp delta k is greater than or equal to alpha for all alpha less than delta. So if you beat everything less than a limit, then you beat the limit. Right? So this is rank. Now, you'll notice that this looks an awful lot like dividing. And basically the idea is, okay, if you have rank 0, then there's no way that I can find instances of phi that are k inconsistent, which are consistent with u. I can't do that. So this is like dimension 0. So, I mean, I guess one way to think about it is if you have a plane, like think about the complex plane, right? C2. Now, in C2, I can choose a formula like y equals mx plus b, like the equation for a line. And as I vary m and b, I can make those inconsistent. You know, like if I choose, let's say I fix m and I vary b. So I fix one slope and then I vary the intercept. Those will become too inconsistent, right? So if phi is of this form, then as I vary b, I can make those too inconsistent. And that means that the rank of the formula xy equals xy in the complex plane has d rank at least 1, because I found some formula which consistent with it, I could break it up into several pieces. Now let's look at the line. Now the line, like y equals mx plus b, that will have infinitely many points on it. And I can break that up further into equations, or I mean into things of the form x equals c, where c is an element on this line. And as I vary c, I break those up into pieces, each of which is consistent. So that shows actually that the original plane had rank at least 2. And okay, the rank is exactly 2 when delta contains formulas to talk about lines. Because instead of talking about lines, I could talk about lines that intersect. I mean, instead of talking about points, I could have talked about lines that intersect the line at a given point. And then the intersection would be just a point. And choosing those distinctly, I could get a bunch of distinct points. And points have rank 0. Okay, so it's some rough notion of dimension. It's like the number of times you divide with delta formulas describes the dimension. Okay, so the 2 observations that we want to make so this is sometimes called the ultrametric inequality, which is kind of ridiculous. Wait, ultrametric inequality or equality, I suppose. Which just says that if I want to take the D rank of, sorry, I don't want to have that one there. If I want to take the D rank of a disjunction, okay, that should be equal to the max from I less than k of the D rank of the disjuncts. All right, so why should that be true? Well, we'll just prove it by induction. So one direction is trivial, since if P implies Q, then the rank of P, delta K, is always less than or equal to the rank of Q. And I leave it to you to check, but it's more or less obvious, right? Because if something is consistent with Q, then it has to be, or sorry, if something is consistent, yeah, if something is consistent with Q, then it has to be consistent with P. So, you know, if you apply the definition to show that the rank of Q is at least 0, then that implies that the rank of P, wait, am I saying this right? Sorry, no, sorry. If the rank of P is at least 0, then that means that the rank of Q is at least 0 because P implies Q. So if P is consistent, then Q is consistent. Now, if the rank of P is at least 1, then I can break up using a formula in delta P into infinitely many k disjoint pieces, each of which has rank at least 0. But doing so automatically breaks Q up into a bunch of pieces, each of which has rank at least 0. So if you prove it by induction, it's a sort of trivial thing, but I encourage you just to do it. It's easy to check. Okay, so that implies that each one of these things on the right-hand side will have rank less than or equal to the rank of this disjunction, because the disjunct certainly implies that, I mean, each disjunct implies the disjunction. And so that means that you have that the max of all the disjuncts is less than or equal to the max of the whole thing. So we must prove that D of the disjunction of K, Cix delta K, is less than or equal to the other side. And how can we prove that? What I really want to say is that we must prove that this being less than or equal to alpha, sorry, greater than or equal to alpha implies that the max of I less than K of D Cix delta K is also at least alpha. So in general, when you prove inequalities involving the dimension, you prove something of this form. So by induction, you prove that if the thing on the bottom side of the inequality is at least alpha, then the thing on the top side of the inequality is at least alpha. Now, how do we do that? Well, so for alpha equals 0, this is clear. If the disjunction is consistent, then one of the disjuncts has to be satisfiable, has to be consistent too. And that means that one of these ranks has to be at least 0. So certainly in the case of 0, it's true. Okay. Now for delta limit, it's also clear by induction. So if I knew that it's true for all of the alpha less than delta, then it should be true for a delta as well. Why? Well, because if I have some delta and I know that that the D rank of the disjuncts being at least, being greater than or equal to alpha implies one of the disjuncts has to be greater than or equal to alpha, then by the pigeonhole principle, as I take a countable sequence, or if I take some sequence approaching that limit, then there have to be infinitely many of the same disjunct chosen. So that means that there's going to be one of the disjuncts which is greater than or equal to alpha for every alpha less than delta by the pigeonhole principle, just because there are finitely many disjuncts. So if I knew that it was true for alpha, for every alpha less than delta, then it's got to be true for delta as well, just by the definition of limit and the pigeonhole principle. So maybe not clear, but by pigeonhole principle. Okay, and so the real work happens at the successor stage. So what do we have to do? We have to prove that, so assume for alpha, and suppose that D of P, oh, not P, sorry, that this disjunction I less than K of C Ix, K is at least alpha plus 1. Okay, then what does that mean? Well, by definition, there is some phi xy in delta and a sequence ai I less than omega such that phi x ai, I less than omega, is k inconsistent? And d of the disjunction of these things together with phi xai, this has rank at least alpha. So before I wrote union, but when it's a formula, it's more appropriate to write conjunction. I mean, the union of two finite sets of formulas is equivalent to the conjunction, considered as a formula rather than a type. Okay, but what is this? Of course, when is a big disjunction conjuncted with a single formula true? That's of course true just in case the disjunction of all of the conjunctions of psi and phi are true. So that implies that d of the disjunction over all I less than k of psi x and phi x ai delta k is at least alpha. This is just propositional logic. Then by induction, this implies that the max of I less than k, or let's say j less than k, just to avoid conflict. I should have said that here, using I in two different ways. That means the max of d cj x ai, wait, no, sorry. D cj x and phi xai delta k is at least alpha. That's the induction hypothesis. So that implies that the max of j less than k of d cj x delta k is at least alpha plus 1 by the pigeonhole principle. Okay, again, so for each I knew that there was some j which realized this maximum, right? So I knew that this maximum was at least alpha. So that means that for each I found some j such that the d rank of cj and phi xai delta k is at least alpha. But there are infinitely many ai's. So that means that for an infinite set of i's, I have to pick the same j to realize that maximum. So passing from my ai's to a subset of them, I find one disjunct such that that disjunct together with phi xai will always have rank at least alpha. And that sequence witnesses that the rank of cj must be at least alpha plus 1. So that gives us the inequality that we wanted. So that's the proof. Okay. So that's a key property. So this tells you that if you work with disjuncts, you really can pick a disjunct. I mean, if you work with disjunctions, you can pick a disjunct to realize the rank. And this is cool because we were studying dividing and we could prove stuff for dividing. We wanted to prove it for forking. Well, if we use rank, then the rank doesn't really see the disjunction. It's actually just going to pick the thing of highest rank. So that's going to be the way that we get rid of this problem. All right, so now let's make some further observations. So one thing to note is that if, so did I number this? Let's see. Observation 1. Okay, cool. So this is like observation 2. All right, so observation 2 will be that if phi x a divides over a, and p is a type over a, then if the rank of dp delta, let's say it k divides, and this rank is finite, it's not infinity, so it has some ordinal, and phi is in delta, then the rank of p union phi x a delta k is strictly smaller than the rank of d delta k. All right, let's think about why. Why? Well, the point is just that you could suppose that dp delta k is equal to alpha for some alpha. Then if phi x a k divides over over a via some sequence I, ai less than omega, then we have d. Okay, let me say it this way. That if d of p union phi x a k delta is at least alpha, then also dp union phi xai delta k is greater than or equal to alpha for all I. Because I is a indiscernible. So it's easy to check that all the properties of the rank are invariant under automorphism. If you take a type and you apply an automorphism to it, the rank doesn't change. Why? Well, because the sequences that you use to witness this at any stage, you can just apply the automorphism to those sequences. So it's very easy to check just from the definition that everything is automorphism invariant. If you apply an automorphism to a type and you move it from one type to another, then it doesn't change the rank. So here we know that all the AIs in our sequence have the same type. And over A, so they're all automorphic images of one another, and that means the rank doesn't change. But then by definition, this implies that the rank of P union phi, of P delta K is at least alpha plus 1. So if the rank didn't go down, then that would mean retrospectively that the rank of dp delta K had to be at least alpha plus 1, but it's also equal to alpha by our assumption. And that's a contradiction. Okay, so if you divide, the rank drops. Okay, now conversely, if Well, okay, let's avoid conversely for a moment. We'll get there in a second. No, I think we do have to say conversely, actually. So conversely, yeah, how does one say this? So what I want to say now is that if you divide, no, I want to say the converse, that if you have an extension that divides, then or no, sorry. So what I want to say that if you have an extension and the rank goes down, then you have to divide. So let's prove that now. So conversely, if Q extends P, so you have two types that extends P, and that the rank of Q is strictly less than the rank of P, which is less than infinity, then what happens, it follows that, then Q divides over the domain of P. So let's say P is like a type in Sx of A, and Q is an extension. So then it divides over the domain of P, which is A. Okay, so how might we prove this? So it suffices to prove that if Q extending P does not divide over A, then the D rank of, then for all delta and K, the D rank of Q over delta and K is at least the D rank of P, like that. And so how do you prove that? We'll just prove it by induction. So assume dq delta k is at least 0, then, or sorry, let's do the p one. Then dq delta k is at least 0. That's true. Why? Well, because if the rank of p is at least 0, then that means that it's consistent. Now, if you take a extension that does not divide, then it's also consistent, because the empty formula, like the formula that is always inconsistent, is a formula that divides. Of course, any indiscernible sequence I look at, even the constant one, if I move my formula along that indiscernible sequence, it's inconsistent, because it's inconsistent, period. So the empty definable set is a set that divides. So if I have something that doesn't divide over A, then of course I have this. All right, so now it's also going to be true for a limit by induction. So the real challenge now is to do the successor case. And what does the successor case say? Okay, so we assume that dp delta k is greater than or equal to alpha plus 1. So there is some phi xy in delta and ai I less than omega, such that phi x ai I less than omega is k inconsistent and the D rank of P union phi x AI delta K is at least alpha. So if we knew Q union phi x AI did not divide over AI, recall that the domain of P was AI, then we could conclude D Q union phi x AI delta K is at least alpha, hence dq delta K is at least alpha plus 1, where this would hold by induction. Because what was the induction hypothesis? It was said that for alpha, if I know that Q is a non-dividing extension of P, then the rank doesn't go down. So why should this be true? So so let's try it this way. I also have to remember how this goes. So let's see if it's easy, and if it's hard, then we can push it off to next time because we're already over time. So if what we'll do is we'll take some B that realizes Q union phi x AI, and our worry is that B somehow divides over AI with the domain of Q. AI. Yeah, okay. So I think the best thing to do is to call this a thing to think about for next time. So we'll try to get this induction to work because we're already over time, so I don't feel so bad about pushing it to next time. And we'll do this very quickly in the first 5 minutes. Then we'll use the rank to prove that forking exists. Then we'll do Kim's lemma, symmetry, and then we'll start in the independence theorem. Then we'll really be doing simplicity theory. So that's very exciting. So I think this rank stuff is kind of grungy. I don't really like thinking about it, but it's important because it's actually the only means we know how to prove that types don't fork over their own domain in simple theories. So, we had these examples where forking and dividing were different, for example, the circular order. And then you had a type over the empty set that forked over the empty set. That can't happen in simple theories. And the rank is the only tool we know to eliminate that possibility in simple theories. And in fact, there are other contexts in which we know that forking should exist over every set, but we also don't have a rank notion, and so we can't prove it. So this is like a big open problem in the field of NSOP1. So this is like an important tool to think about, although we won't use it too much in the sequel on NTP2 and NSOP1 and so forth. All right, so I'm going to stop there. And I apologize I wasn't able to finish this, but I think, it's good to see it over 2 days because then it'll sink in more. And yeah, are there any questions?